principle of strong mathematical induction has a much stronger hypothesis that we assume. Okay. Essentially, it is this. Instead of assuming that one domino knocks down the rest, we assume that all previous dominoes knock down the rest. Okay. All right. So this is useful when sometimes it's not the immediately previous one. Okay. Where maybe the domino 2 before it, or maybe the domino 7 before it is the one that actually knocks down the domino in question. Okay. So we are going to do things a little bit differently. This one does not come up all that often compared to regular induction, which is sometimes called weak induction. Okay, but I'm going to use it to prove one of the most important statements in mathematics, and that is the fundamental theorem of arithmetic. This says every integer greater than 1 is a prime or a product of primes. This product is unique except for the order in which the factors appear. This is what is commonly known as an existence and uniqueness result. So there's the existence of the factorization, and then we'll prove its uniqueness. The existence is when we will use induction. Okay, so I like to say which part I'm doing in my proof. Let's prove existence. Now this is saying it's true for every integer greater than 1, so my base case will be 2. Okay, 2 is prime, so we are done. Remember, I'm trying to prove everything is a prime or a product of prime, so if it's prime, I'm done. Okay, so now our induction hypothesis. We assume that all positive integers less than n can be written as a product of primes, which may just be themselves because they may themselves be prime. Okay, and now we will prove that the same can be said for the number n. If n is prime, we are done. If n is not prime, well, the definition of not prime is that we can write it as the product of two numbers, say a and b. For some integers a and b, with a and b sitting somewhere in between 1 and n. This is why we need strong induction, by the way, because there's no guarantee that either a or b happens to be n minus 1. They might be way much lower than that. Okay? But since I'm doing strong induction, so I assumed a statement about all numbers smaller than n, by our induction hypothesis, okay, a and b must each be a product of primes. And of course, if I take a product of primes times another product of primes, we are done. Okay. This proves existence. Okay. Now, uniqueness is not induction, but I would like to complete the proof of the fundamental theorem of arithmetic, so I will still do it here. Okay. The traditional way to prove uniqueness is essentially a proof by contradiction without formally being a contradiction. So I will suppose that n has two different product of prime factorizations, but then I will prove that they were actually the same all along. Okay. Notice, not only did I label the primes differently, p's and q's, but I subscripted them differently because I'm not assuming that it's the same number of primes on each side. Okay. Now, by Euclid's lemma, as a side note, this is that if p is a prime, if p divides a product, then p divides a or p divides b. Okay. By Euclid's lemma, okay, P1 must divide Qi for some I. Because P1 clearly divides the product of all the Q's, so it must divide one of the Q's. Okay. Since both P1 and Qi are prime, the only way that it can divide, that one can divide the other, is if they are in fact equal. So P1 must equal Qi. So then we do something a little bit fancy. Relabel, okay, so that Qi is really Q1. Just call that one Q1 and relabel all the rest. And then we say, similarly, okay, P2 equals Q2 all the way up to PS equals QS, okay. Now a word about similarly. What this means is, I could have done the exact same argument as I did for P1 with P2. Namely, P2 divides the product of the Q's, so by Euclid's lemma, it must divide one of the Q's individually, and since they are both prime, it must equal that Q. So call that Q Q2. Okay, that's an identical argument, only with a different subscript. This is how we use the word similarly. Okay. Now, I ran through all the P's. Okay, there are no P's left. Okay, so there can be no Q's left. Okay, because I cannot have nothing on the left equal to something on the right. So this also forces S to equal T, and I am done. Not only are all the P's equal, but I have the same number of them on each side. This completes the proof of the fundamental theorem of arithmetic.